So the velocity potential function phi is given here in this expression, that is minus x into y cube by 3 minus x square plus x cube into y by 3 plus y square. So first and foremost we have to find the velocity component in x, and this is the first thing that we need to find in x and y direction. And then we have to represent that this equation, this velocity potential equation, represents a possible case of flow. Okay, so to represent this in possible case of flow, it has to uh, represent the Laplace equation. Okay, now the first and foremost, let us do a partial differentiation with respect to x and y of this equation. So a partial derivative of this phi derivative of phi with respect to x is first and foremost dou phi by dou x. So that is equal to this thing. What we get here is minus differentiation of x is 1, so y cube by 3, differentiation of x square is minus 2x, plus differentiation of this particular one is 3x square, 3x square by y by 3 plus this thing, it is 0 since there are no x component here, so we'll write it as 0. You can cancel this out here, 3 and 3 gets cancelled. Okay, then next one is with respect to y, that is dou phi by dou x is nothing but dou phi by dou y. With respect to y, it will be here x component y, it will be minus 3x y square by 3, so I can cancel this out here again, minus 0 since there are no y component here, plus x cube, differentiation of y is nothing but 1, so x cube by 3 plus with respect to this thing it will be 2y. So I can write it down neatly here, that is 2 phi by dou x here is minus y cube by 3 minus 2x plus x square into y. Okay, so that is what you can write it down, and here we have minus xy square plus x cube by 3 plus 2y. Okay, so here we have partially derived this equation with respect to x and y. Now to find out the velocity component, okay, so first and foremost the velocity component we need to find out. So velocity components are what? U and v. Since there is no function of z here in this particular equation, we're not gonna find out the w as well. So u and v, if you consider this thing, u is nothing but minus dou phi by dou x, so it will be minus the equation that we have already differentiated, that is dou phi by dou x. We need to write it down, that is minus y cube by 3 minus 2x plus x square into y. So minus sign here, and then if you write it down correctly, you'll get as y cube by 3 plus 2x minus x square y. So this is the velocity component of u. Then v is nothing but minus dou phi by dou y, so that is again minus of dou phi by dou y, we have already calculated that. That is nothing but minus xy square plus x cube by 3 plus 2y. So this can be written as x y square minus x cube by 3 minus 2y. So this is the velocity component of u and v. This is a velocity component here. Okay, now let us move down to the next case, that is, will this equation, the expression that is given of phi, does it represent any possible cases or not? To represent this particular flow cases, it should satisfy Laplace equation. So what is this Laplace equation? It is nothing but dou square phi by dou x square plus dou square phi by dou y square. So that is equal to 0. Now we already know that dou phi by dou x is equal to minus y cube by 3 minus 2x plus x square into y. Double differentiation of this particular equation, I'll get dou square phi by dou x square, that will be equal to, since there is no x component, this will be 0 minus differentiation of x, again it will be 1, so it will be 2. Then this differentiation of this will be x square by y will be plus 2xy. Okay, then dou phi by dou y, that is nothing but equal to minus xy square plus x cube by 3 plus 2y. Again dou square phi by dou y square, you will be getting the equation with respect to y, you will be getting minus 2xy plus 0 plus 2. So substituting this in this Laplace equation, what we get here is minus 2 plus 2xy plus minus 2xy plus 2. So this and this cancels out, and this cancels out, so that is equal to 0. So what does this satisfies is that it satisfies the Laplace equation, and hence this phi equation, it represents a possible case of flow.